Hello everyone. Thank you for having me in some conference. My name is Jawher Jerray. Today I'm present a paper doing in collaboration with my colleagues Bastien, Sultan, and Ludovic Apvrille. We will talk about fine-grained confidential and authenticity modeling and verification for embedded system. So for the plane or the talk of today, I will start with the small introduction, then I will present the contribution that we did, including the modelization of security using the tool that we have included this type of contribution. And then I will present also how we do the security verification of some security parameters or security properties. Then I will show an application of our contribution, and I will conclude with the conclusion in the end. So for the context, we talk about the security of embedded systems. Embedded systems are type of system that are made up with hardware and software parts that perform specific tasks. And it is very important to formally verify that this type of system functional well, and including also the security of the system, especially earlier, that's mean before trying to model or to design this type of system. And in this case, there is a need to model this complex system, especially including the security mechanism that can contain this type of system. So the challenge that we have to be met here for our contribution, in fact, when we have now modern threats and this type of threats, that the level of the designing of type of threats is become harder, and this is why the type or the security mechanism are involving. Especially when the threats are also involving. In this case, it is important to model this type of security mechanism and also to verify if this security mechanism goes well what we are needing in this type of systems. So to do that, our solution is especially to take 4 parts or 4 type of verification, especially when we're going to try to support a specific type of security parameters or security patterns, especially when you have multiple security patterns in one single data channel. So if you have one channel and this type of channel contains a lot of security mechanism, it is important to model this type of systems. Also, we need or we add a possibility to verify or to verify each read and write channel or operation. In this case, for each exchange message using these channels, we can verify if this exchange of data verify some security properties. Also, if the security properties is not verified, in this case, we're gonna trace a counter example and we show why this property is not verified. And also, we add a backtracing mechanism that allows to put the results of security verification in the model directly. So all this solution or this contribution that we did, we applied all this modeling system and improvement verification to a tool which is supporting SysML security. So it is a type of diagrams that allows to model embedded system, which we call SysML. So the contribution, including the tool that we used here, first of all, including the security modeling, we used a system or a tool called Diplodocus, and this tool contains exactly 3 modeling views. For the first view is an application view that allows to model the functional aspects of the system. Also, we have an architecture review that allows to model the platform and the hardware parts of the system. And finally, we have the mapping view that allows to allocate the elements of the application view in the architecture. And so if we watch or we present the approach using for the purpose, it relies to the Y approach presented here, the below, and where we have an application view, architecture view, and mapping view. So for the modeling or security modeling, especially in activity diagrams, we have which we call here security patterns. And security patterns, in fact, is the cryptographic operators that allows to secure or to present security, to add security to signals that can be exchanged between tasks. So let me go back here to the application view. The application view to present the system present the functional aspects of the system. We have, in fact, two types of diagrams. We have which called task diagrams, which is approach to block diagrams in UML and SysML. And also for each task, including the system, we're going to present its functional, its behavior using activity diagrams. So we have a set of activity diagrams, and we have an activity diagrams for each component of the system, and we have a global task diagrams that contain each component of the system and how each component will communicate with other components. And including the behavior of each task, we have the possibility to add this type of operators that allow to cryptographic or to add security elements to exchange it messages. And also we have another operator. So we have two types of operator here. An operators for encryptions. We have 5 types of encryption operators: asymmetric encryption, symmetric encryption, MAC encryption, nonce, and hash. For decryption is a single operator that allows to decrypt a message that we can obtain from another task. So here, for the application view and how we present security, how we add security to application view. For the architecture view, when we have to present the platform of an application, among the operators that we can add buses. And for buses, we have two possibilities. We can add private buses or public buses. For private buses, which means a bus cannot be, an attacker has no access to this bus in the hardware stuff, and also but he can also inject and reply to a communication that can made through this bus. However, for public bus, which means an attacker have access to the full access have full access to the data and transfer it via this bus. So this type of presentation allow us to present if a bus is completely public, so the attacker can have access to it, or it is private, which means an attacker don't have direct access to it, but he can like do some injection and reply communication through this bus. Also, to present security in the architecture diagrams, we can map keys in the memories, which mean if we have CPUs that will perform some tasks, the CPUs that is connected with the bus, and this bus is connected also to memory. The tasks have access to the key that is merged, that is mapped to memory. So if we try to merge all this presentation of security and we try to to do little example using this this modeling of security. Here we have we present the contribution that will allow us, or the contribution, especially in the activity, the application view, which means if we have, for example, here in the left, two tasks. Here we have two tasks, one task called Alice and the other task called Bob. These two tasks will communicate to each other using a channel called com here. So if we try to present the behavior of Alice and the behavior of Bob, as showed here in the feature in the right, here in the part left of the feature, we have the behavior of Alice, where Alice try to encrypt a message, then send the message to Bob. Bob will receive the message and try to decrypt it here. For the next part, Alice will try to also Bob will start by sending the nonce to Alice. Alice receive the nonce and using the nonce will encrypt a message that will send it also to Bob. And Bob then he will receive the message and try to decrypt it. So here, as we see, we have security presentation using encryptions and security patterns here in the left part of the activity diagram of Alice. And in the right also we have another security operators that try to decrypt messages from that received from Alice. And one of the contribution we add here also, as we see, for using a single channel called com, we can affect it to several security patterns. For example, here the first send of com is using the security patterns SIM, the first one. However, the second send of this using this channel is using a second security pattern which called SIM-N. So we have two different security patterns that are used for a single channel. And for the architecture view of the system, if we see here, we have CPUs, one CPU that will execute the tasks of Alice, the other CPU will execute the tasks of Bob. These two CPUs are mapped to do different buses. Here we have a private bus where we mapped two keys, the first key for the first set of patterns and for the second set of patterns, and the same thing for Bob. Here we have the two keys. So the two tasks, we assume that they already have exchanged keys before the communication. Also, between this communication, we have a public bus where the data will be sent through this bus. So an attacker have access to this bus. I can also get the messages that is sent from Alice to Bob through the bus. It's the external bus. And so this is the part of modulation. Now we can go through the part of verification of security. For the verification, we have, let's say, workflow that we're gonna follow to do the verification. First, we did the verification, or we did the modeling part of the system using deep purpose, the part that I have presented in the now. And now, after doing the modeling, we're gonna go through is the transformation of the model automatically to another SysML profile, which is using diagrams of block diagrams and also using matchings, and after and also by having security pragmas. Or using these two parts, we're gonna transformate this model also to ProVerif, which is another model checker for security verification that will perform security verification here. And using the results we can have from ProVerif, we're gonna send that we're gonna backtrace it directly to the original model. So after having all this result, we're gonna put the result directly in the Diplocus model, especially in the activity diagrams and in the task diagram. So here, the model that we presented before, we can see that we have the security verification for each send message. Here, for example, for the send message, we verify confidentiality, and also the same for the second pass message. We affirm or we confirm confidentiality. For the receiving of the first message, we only confirm authenticity, but we don't not confirm authenticity. We perform an integrity, but we do not confirm authenticity. However, for a second receive, we confirm both security of authenticity and integrity. And in the final presentation, also here we can see that with the confidentiality always is being verified through these two signs, and only we have the integrity that is verified, but not the authenticity, because the first send of or the first receive of the message here did not confirm authenticity. So if we combine both the two receive of data, combine both, we only have authenticity or integrity that is verified for these two both receiving operations. So here also doing this security verification, we do auto generation of security pragmas, which means we only have to mention the channel that we have to verify his security, and and after that only all the security pragmas will be generated automatically and we verify it one by one to confirm if each send and receive is verify some security properties. And also this approach allow us to present a counter example for verification for properties that not verified. For example, here authenticity is not verified, so we can show an example using sequential diagrams why this example is not verified. As in a verification or as a use case study here, we present an example for an exchange of data between two tasks for automotive network. The two tasks are engine control and the braking system. And this exchange of data will be through one channel we call it COM. And we have two type of messages that will be sent. First of all, we have a message that contain sensitive diagnostics that have to confirm confidentiality and integrity. And the second one, we have breaking commands that we have to confirm authenticity. So if we have to show, first of all, to model this system and then verify if these two properties of security are verified, we need first to use our approach. So to use our approach, we have to, first of all, start by modeling the system using the Diplocus, and then perform the security approach to backtrace the result directly in the model. So if we follow the approach, first of all, we need to start, as I said, first step to model the system. Modeling the system needs to have the application view of the system. So we have to perform or to model the task diagram of the system. We have two tasks here, engine control and braking system. These two systems will be communicate through this channel COM to terminate the communication. Then for each task here, we will present the activity diagram, the behavior of this task. For the first one, we have two type of messages that we have to send: diagnostic diagrams and breaking controls. The first one need to verify authenticity and confidentiality. So we need to present. We use pattern of security that allows that, which is symmetric communication or symmetric encryption. For the second one, we're going to use the nonce and also using the MAC communication. For the second, we do the same thing. We present the system for breaking system that will receive these messages. And also we terminate that by modeling the architecture and the mapping diagram of the system, which allows, as I said, to present the different parts, the hardware parts of the system. When we finish by the modeling the system, we start by another task will be due automatically, which is transformation of this task of this model to another type of model, which is avatar model. This avatar model is suitable with security verification. That's why we do this transformation. So automatically we will have the same model or the same system using block diagrams, and also using machines of each block. Once this part is finished, then automatically this models will be transferred to ProVerif models or ProVerif specification, also to a set of queries. So all this one will be presented through ProVerif file. That this file will explain the specification of the model, and this file is generated, as I said, automatically. Once we generate the file, we will run then the model checker of ProVerif that will verify if the set of queries is verified or not. Once it is done, then we will go through the next part, which is to parse the results of the results that we obtained through the ProVerif's model checker, and finally we'll finish by backtracing the results to the model. In this case, we will find the results directly to the model. So here, for example, the confidentiality is not verified because the second send did not need confidentiality, and for the receive here we have only integrity that is verified because authenticity is not needed for the first one. So the backtracing also is presented in the activity diagrams, as we saw here. The first send confirm confidentiality, but not the second. And for the receiving, authenticity is verified for only for the second one, and integrity is verified for both receiving of messages. And also, as a result, we can obtain attack trees for examples that for properties that not verified. So here, for example, an attack tree for why the result is not verified for the authenticity. So as a conclusion, we here present a technique is to identify security attacks by modeling security aspects of a model, also by backtracing the results directly to the model. And this type of security can contain multiple security patterns in a single channel. Also, we can have a lowing fine-grade verification for each receive and send operators. We implement this technique to a tool called the Diplodocus that allows to model embedded system. And we show that this approach can be used for different systems. For example, as I mentioned here, the system of automatic network system. As a future work, we want to extend this approach to support other type of modeling and other type and additional security properties, more than confidentiality, integrity, and authenticity, and also to explore other method to help designers to automatically specify security features, for example, using AI. Thank you for your attention.